I think you're going to love this last part on rational functions because I'm going to show you some shortcuts for graphing some certain rational functions. I'm also going to teach you about slant asymptotes, and that's just good stuff. The first thing you want to know is how to graph the basic rational function 1 over x. And this is the graph, the one that you're looking at. Just think about it like if you plug in x equals 1, 1 over 1 is 1, and 1 over 2 is half, so the y value is half right there. 1 over a half would be 2. So those are some nice points that we know. Usually I just focus on the point 1, 1. And then this has nice origin symmetry, so you'll notice that we've got those same points only down in the third quadrant. Well, we're going to use that idea to graph transformations of functions. This first one, 3 over x, that's the same thing as 3 times 1 over x. In other words, this is going to be one of those vertical stretches by a factor of 3. So instead of our function having points at 1, 1 and -1, -1, it's going to be a vertical stretch, so the y value is going to be multiplied by 3, the y value multiplied by 3, and those asymptotes aren't going to change because 0 times 3 is still 0. So that's just a rough graph, but that's all I'm really looking for. I just want to see where those key points wind up after the stretch. We'll try another one here. This time we have our basic function plus 4. So that plus 4 not happening to the x value but to the entire function, so that's a y plus 4. It's going to move everything up 4 units. Now originally the graph had an asymptote at y equals 0 and a vertical one at x equals 0. So when we do a translation 4 units up, our new asymptote will be 4 units up. The vertical asymptote stays put. So I'd be looking at my 1, 1 actually being up at 1, 5 now, and -1, -1 at -1, 3. And so then you can sort of picture how that whole graph has just been shifted up 4 units. Just a nice quick way to get some basic rational functions graphed. This last one, we're going to have a reflection, and that's a vertical reflection up and down. And then this is sort of grouped in with the x, so that's going to be a horizontal shift 2 units to the, and this time it is left. The +2 indicates that we're going to move to the left. Maybe we should just look at where those 2 main points are going to flip to. So first we're going to flip those vertically. So that first one flips down, the second one flips up, and then we're going to shift those guys over 2 units, 1, 2, 1, 2. You can think of that asymptote that would usually be at x equals 0 to now be at x equals -2. Our horizontal asymptote won't change because reflecting it or moving it right and left stays in the same spot. So here's our new graph. It's going to look like it's reversed because of that reflection. And then again, we've moved it 2 units to the left. The other basic function that's worth looking at is 1 over x squared. 1 over x squared is always going to be positive, right? Because even if I stick a negative number in, -1 squared is +1, 1 over 1 is 1. And so we're going to have 2 key points at 1, 1 and -1, 1. Some other key points you might want to think of are when you plug in a 2. 1 over 2 squared would be at 1/4. And 1 over 1/2 squared would be at 4. So those are some of the points that I sometimes look at. -2, 1/4, and -1/2, 4. Again, just mostly focusing on these 2 points. Here we've got something happening to the x value, so horizontally we're going to move that 2 units to the right. And because we used to have a vertical asymptote at 0, moving that 2 units to the right, our new asymptote will be at x equals 2. Moving things left and right is not going to affect that horizontal asymptote, so that's going to stay at y equals 0. And then our key points are going to be what used to be 1, 1, but now is 3, 1. And what used to be negative 1, 1, which is now positive 1, 1. And then we can just sort of sketch in the rest of that graph. I thought this one would be fun to do because we've got a multiplier next to our x value, right? So that's going to be a horizontal stretch or shrink. Since it's a 1/4, that'll be a stretch, kind of opposite of what it seems. So that's a horizontal stretch by 4. The reciprocal of 1/4, 4. So we're going to see some stretching on the x values, but those asymptotes won't change. Where we would have originally had our points, just think that we are going to horizontally stretch those times 4. So the x value times 4 will move those out to 4, 1 and negative 4, 1. I think I am going to think about those other points. Remember how we had points at 1/2, 4 and negative 1/2, 4? Well, if you multiply the x value, the 1/2 times the horizontal stretch of 4, those are going to be out at 2. That just kind of helps me see how fast it wants to come into that other asymptote. So it's making it in there slowly. But you'll see that this graph looks a lot wider, right? Because it's got that horizontal stretch going on. And then the last one has a few things. So here's my parent function. I've got a negative out in front, which means I'm going to reflect vertically. And then this -2 out in back, also a vertical, meaning we're going to go down 2. So normally I would have points here and here. But we're reflecting those, a vertical reflection across the x-axis then. And we'll also be moving those down 2 each, down 2 each. The asymptote used to be at y equals 0. If we move it down 2, it's going to be down at y equals negative 2. Vertical asymptote doesn't move. And our new graph is an upside down looking function that's also shifted down. I just think it's great how we can make good sketches of those graphs without going through all of the whole 7-step process. So that's kind of nice. Slant asymptotes, they're so cool. Look at this graph. It's got sort of like a vertical asymptote at x equals 2. And you can see that from the graph, right? At x equals 2 would have a vertical asymptote. But doesn't it look like there's also sort of an imaginary slanted line that this is following? That's called the slant asymptote. I know what you're thinking. How can I find the equation of that slanted line? You're going to use division. You can either use long division or synthetic division. Let's try it on this function. So we're actually going to take that x squared minus x plus 2 and divide it by x minus 2. If we wanted to go synthetic division, we would use a positive 2, 1 negative 1, 2. And we don't get a 0 remainder or anything. Basically what this is saying is that we could rewrite the function as f of x equals, so this would be our number, this would be our x, that's our remainder. It would be 1x plus 1 plus 4 over x minus 2. The idea here though is that as the x values get bigger and bigger, or negative bigger and bigger, 4 over some giant number is basically going to be nothing. So you are going to disregard the remainder. What we just found is that the line y equals 1x plus 1, or y equals x plus 1, is the slant asymptote. So let's graph y equals x plus 1, a y-intercept of 1, and then it goes up 1 over 1, up 1 over 1. And that's our slant asymptote. Amazing. Just a quick little division and you'll have the equation for that line. When can we expect to have a slant asymptote? Well, you know how when you're checking for horizontal asymptotes, you compare the top term to the leading term on the bottom? And remember that if it sort of cancels out and we get an x, then there's no horizontal asymptote. But the fact that that x came out when that degree on the top is higher than the degree on the bottom, that's when you're going to have a different type of asymptote. So when the degree on the top is 1 more than the degree on the bottom, you'll find a slant asymptote. We'll just do a quick run through on how you could graph one of these. So the y-intercept, we're going to plug a 0 in for x. And if you plug in a 0 for x, don't you get 4 over 0? That just means there isn't a y-intercept. And how can we make the top equal 0? How can we make this equal 0 on the top? Negative x squared plus 4 equals 0. It's looking like plus and minus 2 would give me a 0 on the top. My vertical asymptote, where the bottom is 0, would be at x equals 0. There aren't any matching factors on the top and bottom, so no holes. Horizontal asymptote, I would compare the negative x squared on the top to the x on the bottom. The x's cancel out, but that indicates that we don't have a horizontal asymptote. But again, since that degree on the top is 1 higher than the degree on the bottom, we do have a slant asymptote, and we're going to find that using division. Long or synthetic, it's totally up to you. Now, when you think about this, we're actually dividing by sort of like x minus 0. So 0 would be the number that you'd put in the little box. Don't forget the placeholder since there's no x term. And so what we found out is that we could rewrite this function as negative x plus 0 plus 4 over x. And as the x's get huge, this term goes away, we disregard, and all we'd have left is the y equals negative x. That is our slant asymptote. And we'll put some of this on the graph and see if we can get an idea of what this would look like. The line y equals negative x just has that negative 1 slope, down 1 over 1. So there are the asymptotes. It looks like we might have some symmetry. It would probably be origin symmetry, right? Can you imagine flipping this graph upside down? As of right now, it's looking like it would look the same upside down. Let's just maybe try another point or two. You know, the points I like to try, the ones that are near the vertical asymptote. So I think I'm going to try a -1 and a +1 and just see how those come out. I'm getting -3 for that one. And +3 for that one. I think this is an origin symmetry, an odd function, right? And so if I follow those asymptotes, it's looking like the graph will look like this. And like this. So I am seeing that origin symmetry. I feel like we should probably prove that this has origin symmetry by doing that little replacement trick, right? Do you remember how to do origin symmetry? We're going to replace the x and the y with a -x and a -y. So we'd have -y equals negative x squared plus 4 over -x. This would just come out as negative x squared plus 4 over negative x. And if I divide both sides by negative 1, I'll apply that to the bottom of the fraction. And it does come out exactly the same as it was. And so that proves that I've got that origin symmetry on this one. I just think those are fun looking graphs. Let's try an application problem. I really like this type. It's about how much it costs you to produce a product. And usually there's some sort of startup cost. Maybe it's like the factory equipment or whatever. So here we're producing a pair of shoes and there's a startup cost of $40,000. And once you pay that, then you can start making pairs of shoes for $40 each. And so we're going to write a function c of x that represents the total cost to produce x pairs of shoes. C of x would just be that $40,000 base plus $40 per pair of shoes. So that's our cost function. What we want to think about is how much each pair costs. We want to think about the average cost. So to find the average cost, we would just take that total cost and divide by how many pairs we're getting. So we're going to call that C bar of x. So we're going to take the total money that it's costing us and split that equally amongst each pair, and that will be our total dollars per pair for each pair of shoes. And that's a rational function, which is kind of fun. Let's try plugging in a few values for x. So C bar of 100. Definitely just going to use my calculator to do that. I'm getting 440. C bar of 500. 120, and C bar of 1,000 is 80. And what do those represent? Well, I know that the x value represents pairs of shoes, right? And the C bar function represents the average cost per pair. This seems kind of crazy because I just told you it costs $40 to produce each pair. But if you're only going to produce 100 pairs, you could think of that as each pair costing $440 since we're splitting the cost only amongst 100 pairs of shoes. This C of 500 means that if we up the production to 500 pairs, then they'll cost an average of $120 per pair to make. The more pairs you make, the lower that cost is going to come, right? So as our x value gets bigger, our y value, I guess it's not f of x, our y value, our cost per pair is coming down to somewhere. Isn't this the notation we used for horizontal asymptotes? So that's what the next question is about. Where does C bar of x have a horizontal asymptote? So we would take the leading term from the top and the leading term from the bottom and compare those. And it reduces to 40. So what that means is that y equals 40 is our horizontal asymptote. So as x goes to infinity, the y value goes to 40. What does that mean? As we produce more and more and more pairs of shoes, our average cost is going to get closer and closer to that actual $40 a pair because we'll be splitting that fixed cost among so many pairs that it'll become negligible. So what that tells me is that the more pairs of shoes that I produce, the less they will cost. It'll never go below $40, but it'll get closer and closer to $40 each. A nice application of rational functions.